So good afternoon, everyone. First of all, I would start with thanking the organizers for giving me opportunity to present my work. So today I will be talking about computing quantum phases in Kagome metals AV3SB5, where A can be potassium, rubidium, and cesium. So I'm heading currently a quantum materials lab at Department of Physics, IIT Ropar. My research in a nutshell. So at IIT Ropar, I'm currently doing these projects. So basically, my work focus mainly on the growth, where I grow polycrystalline as well as single crystalline materials, quantum materials. Then my expertise lies in MUSR technique at ambient pressure as well as at different pressures. Then probing the charge density wave, spin density wave phases, determining the superconducting gap symmetry in unconventional superconductors, and then tuning the different phases through different tuning parameters, including pressure, doping, and even strain. Then my recent focus is on this growth of this van der Waal magnetic as well as topological materials, and also the Kagome lattices. And I will talk more about the Kagome lattices in today's talk. So basically, this work which I will be presenting is mostly done in my postdoc, because so our group is recently new, 2.5 years. I have joined IIT Ropar. So I'll be presenting probably next time. Uh, Starting with the Kagome. Uh, so this Kagome is a Japanese name for the woven basket. So if you look here, if you look at the structure of this basket, and if you compare with the structure of one of the compounds, cesium vanadium 3 antimony 5, so you can see you have vanadium cations which are coordinated by the octahedra of antimony. So if you look at the structure of vanadium, how they are interacting with each other, so it extremely looking like this basket structure. That's why they have this, they are known as the Kagome lattices. And because of this very interesting geometrical structure, they have inherent frustration into them, and due to that they show several non-trivial features in their band structure, including the Dirac like crossing, Van Hove singularities, and flat bands around the Fermi level, which is indeed observed also in the ARPA studies. And because so many non-trivial features are there around the Fermi level, so there are many interesting phenomena, physical phenomena are happening in these compounds, including the charge order between 75 to 110 Kelvin, followed by the superconducting transition between 1.2 to 3 Kelvin, and then topological features. And related to that, people have observed gent anomalous Hall effect. So these material class is extremely interesting, and it will be interesting to see the superconducting gap symmetry in presence as well as in absence of the charge order phase. So what happens to that? And to determine the superconducting gap symmetry, I have used MUSR technique. So before going to the MUSR technique, I'll just uh, tell you briefly about the sample. So I will discuss mostly my result on the cesium vanadium 3 antimony 5. So these are the crystal which we use for MUSR studies at ambient pressure as well as under pressure. So this compound, the optical picture, so these were grown using the flux method, and you can see a very beautiful hexagonal symmetry of this crystal, which is visible in the optical picture itself. And then Lave and the Lave showing the hexagonal symmetry, and then this XRD showing that the crystals are grown using along the C-axis. So you can see in the magnetic susceptibility a drop around the 94 Kelvin, and a kink in resistivity, which is because of the charge order formation. This is because the charge, whenever the charge order phenomena happens, there is a partial reduction in the density of state, and that is the reason that there is this decrease in the magnetic susceptibility and a kink in the resistivity. and followed by a superconducting transition, which can be seen as a diamagnetic shift in around 2.5 Kelvin, and a drop to zero in the resistivity, which is happening a slightly higher temperature, but that might be because of some filamentary channels present in the sample. So these well characterized samples were then used for the MEOSAR studies. So now comes what is a MEOSAR technique. So basically the name is muon spin relaxation and rotation technique, and we use muons here. So why muons are like interesting? Because if you look at the property of muon, they are the plus E or minus E charge particle. If you look at the mass, here comes the interesting part. So the mass of muon is 206 times of mass of electron, but it is 9 times lighter than the mass of the proton. And if we look at the lifetime, it's 2.2 microsecond, and the magnetic moment is very high. Okay, so because of high magnetic moment and a very small mass, the gyromagnetic ratio is very high, and that is the reason this with this technique we can detect even a tiny amount of magnetic field present in the sample. So that's how the muons are being used. Now how they are produced? So basically you bombard highly energetic protons, 600 to 800 MeV protons on light nuclei, which is typically graphite, and there they produce pions. These pions are highly unstable particle having a lifetime of 26 nanosecond. So they decay further into muon and neutrinos. So these muons are then used for the experiment. Okay, so basically why these muons are being used? So if you look here, so this pion which decays at rest, so it's and also the spin, if you look at the spin, it has zero spin. So pions which are decaying at rest, basically if so since they are decaying at rest, their angular momentum has to be zero, I mean the total angular momentum has to be zero. So the muon and the neutrino has to go in the opposite direction, and now we know that the only left handed neutrinos are possible in the nature, right? So that means the spin of this neutrino which is coming out should be opposite to the to its angular momentum, and the total angular momentum of the initial pion is zero. So that means this muon has to be also have the angular momentum opposite, sorry, spin momentum opposite to its angular momentum. So that means by using this we can get 100% spin polarized muon, and that is the key feature of the MEOSAR technique, which is being used for the MEOSAR experiment, that we have 100% spin polarized muons. And now these 100% spin polarized muons are basically uh, okay, so they are basically bombarded in the sample. So this is the schematic of the experimental setup which is being used. So these 100% spin polarized muon beam comes inside and interact with the sample's magnetic environment, and you know the lifetime of muon is 2.2 microseconds. So after that it decays into a positron and to neutrino and antineutrino. So basically uh, so if you have a magnetic field in the sample, so this muon spin will precess around the magnetic field, right? So we are not detecting, of course after 2.2 microsecond these muons will be decaying into positrons, and this is observed that the positrons are emitted preferentially along the spin of decaying muon. So basically by looking at number of positrons at particular time, you can basically determine the polarization as a function of time. So this is what one see in a typical MEOSAR spectra, and basically you can do measurement in three different configuration. In one case you apply magnetic field perpendicular to the muon spin direction, in one case you apply parallel, and third case you do not apply any magnetic field, you do the experiment in 2-0 field. So basically these type of experiments are important when you are looking for very tiny magnetic field. For example, if you are looking in a superconductor some internal magnetic field because of the time reversal symmetry breaking. Um, So these are the three configurations. And now for uh, okay, so in case of a superconductor, how this technique is important in determining the superconducting gap symmetry. So I will be talking about the type 2 superconductors. So basically, if we apply a field in the vortex state, that means between Hc1 and Hc2, so you know that the magnetic field will start penetrating through the material in the form of vortices. And if you look at the field distribution, this is how it should look like. So the peak is showing the position of the vortices. So you see the muon which is bombarded in the superconductor in the vortex state, they will see three different fields. So some muons they can stop inside the vortices, some muons they can sit between the two vortices, and some muons they can sit between the three vortices. So they experience three different field. And related to that, you will see when the muon will be sitting between the three vortices, you have a cutoff, and then muons which are sitting between the two vortices, you have a saddle point and then a tail at the higher field. So basically, this asymmetric line shape you should see if you have a well defined vortex lattice in your material. And as I said, this muon spin polarization as a function of time, this is what you see in a MUSR experiment. And if you take the Fourier of this, so this will tell you about the field distribution. And if uh, it is a paramagnetic state, you will not see any damping, because your muon is experiencing only one field, whatever you apply from outside. So you will see a sharp, very sharp peak. But if it is in vortex state, as I explained to you, you will see muon will see three different fields. So then you will see, of course, if your crystal is like very pure, very high RRR value, in that case you should see this asymmetric line shape. But if you have a polycrystalline sample or not very good single crystal, in that case, of course, this asymmetric line shape effect will be masked, and you will see broadening. So the value of if you look at the peak position, this will give you the frequency, the value of field which is experienced by the muon, and the damping in this peak will tell you about the field distribution or dynamics in the system. So basically, in a superconductor, this width of this peak basically is directly related to the inverse square magnetic penetration depth, or I can say the superfluid density. So if we collect spectra at different temperatures, so basically you have superfluid density as a function of temperature, and then you can use different models, to uh, tell which type of superconducting gap symmetry in your system, right? So with the basic of MUSR technique, let us move to the sample which we study, cesium, vanadium 3 So we did experiment in two different configurations. One, we applied magnetic field perpendicular to the Kagome plane, and the second we applied magnetic field parallel to the Kagome plane. And I just have shown this spectra for two temperatures, 5K, which is well above the transition temperature, and then deep inside the superconducting state, which is 270 millikelvin. So you can see this spectra is, damping is less. There is slight damp signal. This is because of nuclear magnetic moment present in the system. And then this further, if you look at 0.27K, it is very much damped. This is because of the inhomogeneous field created due to the vortex formation, and same goes for B external parallel to the Kagome plane. And if we take the Fourier spectra, so you see this is the 5K one. Of course, you should see a peak, but as I explained, there are nuclear magnetic moment present in the system. But if you look in the superconducting state, this spectra is rather asymmetric in nature. So this shows that crystals are of good quality. But for this field direction, we see the broadening in the signal, but we did not see the asymmetric line shape of the signal. This is because when you apply B external parallel to AB plane, so the screening current will flow in the AB plane, and eventually you will determine the magnetic penetration depth in the AB plane. And if you apply external field perpendicular to the AB plane, so one of the component will be along C axis, and the penetration depth along C axis is greater than the penetration depth along the AB plane, and that is why you see elongation in the vortex lattice. One schematic is shown here, and that is the region that you see this broadening. Okay. So by doing the fitting, we estimated the broadening in the field distribution, and this is shown here for two different fields, for field directions, and also the internal magnetic field for sensed by the muon for two different direction, and you can see a clear drop showing the diamagnetic shift. So one interesting parameter which one can look into is this skewness parameter. So this is nothing but the ratio of one third power of third moment of the field distribution and square root of second moment of field distribution. So basically this is a measure of skewness, I mean asymmetric line shape. So if this ratio is close to 1, that means you do not have, I mean your vortex lattice is well aligned, well formed. But if you see different value, that means there might be some vortex melting. So that kind of feature one can see. In our case, we see a constant value of the skewness parameter, which rules out the possibility of vortex melting. So by subtracting this nuclear magnetic contribution, we are left with the only the superconducting contribution, and this superconducting contribution is directly related to the inverse square magnetic penetration depth through this Brandent model. So these are the parameters which are known from other techniques. So we could calculate the inverse square magnetic penetration depth along the AB plane and along the C axis, and both of them are plotted here. And we tried to fit using different models, and we could fit our data reasonably well with the multi-gap S plus S model. So showing the multiband nature of superconductivity, which is further supported by this anisotropy parameter which I plotted here. So basically if you look uh, within the Ginzburg-Landau model, this anisotropy in the penetration depth, which is nothing but lambda c by lambda AB, and anisotropy in the upper critical field, they should both be equal for a single band superconductor. But here they show a different temperature variation, uh, which shows which further confirms the multiband nature of superconductivity. So these results are shown here are at the ambient pressure. But what happens when you apply pressure? So if you look at the phase diagram existing, so this charge density wave phase, this is suppressing with pressure, and it completely disappears around a critical pressure of about 2 GPa. And we see a high value of Tc about 8 Kelvin around this critical pressure, which is understood because when the charge density wave phase is suppressed, so the charge carriers which were depleted because of that, they are now available for to participate in the superconductivity phenomena. That's why Tc increases. But what is happening around this this first critical pressure P1? So you see a double dome like feature. This P1, what is happening around P1 was not very well understood, and the same feature you see also in the upper critical field. Uh, uh, I mean, as a function of pressure. So also they have plotted this d rho by dt as a function of temperature. So this step like feature in the charge density wave around the charge density wave transition changes to the dip like feature around the same critical pressure. So that means it has something to do with the charge order phase. So that is why we carried out the experiments under pressure, and this is the pressure cell which was being used. I will not go into much details, and we can reach up to pressure 2.5 GPa at low temperature. And before going for the actual experiment at the beamline, we do ACS susceptibility measurement. We put one pressure indicator along with the sample, and we determine its Tc at low temperature, and that's how we calibrate the pressure. And this is the beam line which was being used. So here, other beam lines, the muons are produced from the pions which are staying at rest, but here the muons are produced from the pions which are decaying in flight. That means they give their extra momentum to the muons, because we need highly energetic muons to penetrate through the thick walls of the pressure cell. So we again carried out different experiment, different spectra, I mean we took, and then at different temperatures and different pressures. So this is the summarized graph of inverse square magnetic penetration depth as a function of temperature. And we have also summarized the transition temperature values and the inverse square magnetic penetration depth, which is directly proportional to the superfluid density for a clean sample. So you can see the double dome like feature also in this superfluid density. And also the whole range, whole pressure range, the data could be fitted well with the multiband nature of superconductivity. That means superconductivity is not changing its nature. So something is there with the charge order phase. And one interesting feature we see is this double step like behavior here. And this pressure 1.68 GPa, this lies exactly between these two regions, region 2 and region 3. So it shows a first order phase transition, because some of the part of the sample is observing a slightly lower pressure, so they are seeing the lower TC in this range, and some of the part is seeing higher pressure, slightly higher pressure. So this feature is providing you the evidence that this is a first order phase transition. If we plot this famous Yamura plot, which is between TC and superfluid density, in region 1 and region 2 you have two different slopes, and region 3 of course there is no charge density wave. This is completely suppressed beyond this pressure 1.74 GPa. So region 1 and region 2, two distinct uh, uh, slopes are telling you that there are two distinct competing nature of charge order phase and superconductivity happening in these regions. We could not understand it with the um, experimental method, so we tried with the DFT calculations. And there you see this parent one, which is the Kagome, perfectly aligned Kagome lattices. And then these are the suggested models for the charge density wave, planar trihexagonal, which involves M point instability, Star of David, which involves both M and L point instability, and then staggered trihexagonal, which involves M and L both. And the periodicity for charge density wave order will be 2 cross 2 cross 2 for both of them. And for this it will be 2 cross 2 cross 1, which is not observed experimentally, so we can rule out the possibility for this one. And if we look uh, in the enthalpy difference between the two of them, it is not much. So that means any of the phase can switch into each other within the pressure range we studied. But if we look at the density of state at per formula unit, so this Star of David phase has higher density of state, that means higher TC, and the staggered trihexagonal phase has lower density of state, showing the lower TC. That means this is the phase which is most probable in region 1 where we have higher TC, and this is the staggered trihexagonal should be in the region 2. So we have two distinct charge order phase in region 1 and region 2. uh, One more, so how much time? Okay, so just 2 minutes maybe. Okay. Okay, so basically we carried out zero field experiment in three different regions of the phase diagram. And here we see some step like feature around the superconducting transition temperature, but we know that the charge order phase in these compounds, they are breaking time reversal symmetry, so there is a magnetic field already present. So this might be because of the Meissner screening of those magnetic field, there is actually no time reversal symmetry breaking. But in region 3 where there is no charge order phase present, we see, you can see a continuous change in the electronic relaxation rate, and there is no reason to believe that time reversal symmetry is broken because there is no competing charge order phase here. So this is a very interesting new observation, and I followed some articles, they are claiming something S plus ID type of superconducting gap symmetry. But yeah, that is a still open question to follow up. Of course there are many other things, but yeah, I mean, I will just say that these materials are really interesting to study the unusual interplay between the chiral charge order and the superconductivity. And the superconducting gap symmetry is highly unconventional, and there are much more to explore in this system. With that, I would like to thank, of course, my PSI collaborators. They are the coolest group I have worked with, and of course my group at IIT Ropar. They are working on currently many projects which I discussed in the beginning. And I would like to thank my funding agencies, first of all IIT Ropar, DST, and NRF for providing me money to do all the research. And with that, I would like to thank you and happy to take questions.
Thank you very much. The floor is open for questions now. Any question?
You have shown like when you fitted the curve of superfluid density, that is S plus S wave nature.
Yeah.
So have you done some experiments to check the strength of each bend? So I think when you apply the pressure, then the band strength changes.
Yeah.
So have you done some experiments to check the band strength?
Okay, so basically there were already, of course, experiment. I mean, there are already STM studies and other studies done on this compound, and we compare our gap value, what we obtained from our fit, and they were pretty much in coherence with the already experimentally observed. Because from here we cannot directly from using MUSR we cannot directly look at the strength of the gaps and other things. We can do only the fitting, and then from there only we can say something.
Another question is in vanadium system, I show that applying field may change the pairing symmetry.
Mm-hmm.
That was a nodeless there at some applied pressure, and that there was a nodal pairing symmetry also.
Mm-hmm.
So I'm little curious, like how pressure can change the pairing symmetry there.
Okay, so of course with the so which one you are talking about?
Vanadium, just last slide, I think.
Okay, so
Yes.
yeah, probably this one. So basically, yeah, we are changing from nodal to nodeless, and of course there are many with pressure we are basically weakening the whatever the Fermi surface nesting is there. And then of course, since charge density wave and superconductivity, they are in competition with each other, right? So I mean, in principle, the superconductivity can change nature if the charge density wave order at different pressure will compete differently, right?
So thank you, Ritu, for
Hi,
this
Rati.
interesting talk. So regarding this charge order, chiral charge order, and the interplay between the chiral charge order and superconductivity, usually muon is only sensitive to the so the magnetic degrees of freedom, right?
Yeah.
So from out of this to make some kind of information about the chiral charge order things, how do you connect these things in general?
Yeah, so basically you rightly said that if you have a charge order phase, it is associated with the instability of charges, so you should not see anything around, right? But in this case we see indeed see, like I'm not showing the high temperature data, but maybe it is somewhere. Yeah, so there we see changes around the in the high temperature range. If you see around the CDW transition, we see sudden changes in all the relaxation rates. So that was also to our surprise, that how a charge order phase. But then we looked deep into it, and it is because of the chiral type of charge order. So we have orbital loop currents present, and they are giving rise to some magnetic field, and that is giving rise to the the enhanced this muon width.
So that means if I have understood correctly, so if we have a charge order, so that means if the chiral degrees of freedom, you're thinking. So that is actually developing some kind of
Exactly.
tiny internal field.
Exactly.
And that tiny internal field is it static or is dynamic?
Okay, so we can look at different I mean that part is still not very well understood, but mostly the changes are being observed in this static part, like the sigma one, not the electronic word. So I would say maybe static, but not completely, I would say.
Okay, if there are no further question, thank you. Let's move to the next talk.